With each fascinating picture captured by the James Webb Space Telescope, it keeps on gathering contemplations from various corners of the universe, including planets within our own planetary system. A year earlier, we thought about our most significant brief sea pictures showing the Kina Nebula, the Stephan Quintet, and additionally, strikingly, the enchanting Deep Field image. This express picture clearly depicts different galaxies resting in the vast extent of the universe, fulfilling the doubts made. The James Webb Space Telescope hasn't stopped being a maze. It has, in fact, uncovered objects that test deeply grounded cosmological hypotheses. These astonishing revelations are now being named universe breakers by cosmologists, frustrating established experts with their ability to challenge existing theories. The reasons for these discoveries remain shrouded in mystery, throwing our theories and hypotheses into disarray. So what's the latest scoop from the James Webb Space Telescope? What remarkable new discoveries has it revealed that were previously unknown to us? Join us as we dive into the revelations of how the James Webb Telescope has presented evidence proposing the presence of another universe, testing the standard understanding of the Big Bang. Our universe, as we've long known it, rose from a hotter, denser state by means of a theory known as the hot Big Bang. This thought, a significant scientific achievement throughout the past century, gained overwhelming support during the 1960s with the discovery of the cosmic microwave background, CMB, an echo from the early hot and dense state. Over time, the Big Bang has remained the winning theory explaining the origins of our universe. All things considered, new and fundamental insights have led cosmologists and astrophysicists to re-examine both the ongoing expansion and the Big Bang itself. Despite these challenges, alternative theories have failed to gain traction, with the prevailing theory of the universe's origin enduring. According to the dominant view, the universe began as a smaller, denser universe in the distant past. The presence of radiation such as photons shows that the universe was hotter at its beginning and has since cooled. Extrapolating backwards in time, the density, temperature, and energy levels varied, where a singularity could form and the laws of physics would break down around 10 to the power of minus 43 seconds. In such a short span of time, microscopic distances, short timescales, and high energy levels challenge our understanding. Rewinding the cosmic clock to the speculative zero point, if the universe began as hot and dense, it would have expanded and cooled, producing vast amounts of particles and antiparticles, with excess particles being destroyed by radiation. As temperatures decreased, the breakdown of the electroweak and Higgs forces led to the formation of the four fundamental forces and particles with non-zero masses. As the universe cooled further, protons and neutrons formed composite particles called quarks and gluons. The combination of protons and neutrons led to the formation of light nuclei such as deuterium, helium-3, helium-4, and lithium-7. Overdense regions underwent expansion due to radiation pressure, followed by gravitational collapse leading to the formation of large-scale structures. About 380,000 years later, the discovery of the cosmic microwave background many years ago established the theory of the Big Bang as the most supported explanation for the universe's creation, describing the early universe as a hot, dense soup of subatomic particles gradually cooling over time. Big Bang versus steady-state theory. While most cosmologists and astrophysicists embraced the Big Bang theory, staunch defenders of the steady-state theory, such as Fred Hoyle, continued to support increasingly doubtful ideas, only to face defeat in the face of overwhelming evidence. The proof presented was conclusive. It wasn't dimming starlight or reflected heat from dust. The celestial glow displayed remarkable consistency, resembling a perfect black body, yet had no connection to known objects in the universe. Despite this, Hoyle and his allies continued to undermine scientific progress by backing scientifically dubious ideas. Meanwhile, the fields of space science and cosmology underwent significant changes from the 1960s through the 2000s, with cosmology making particularly vital strides. We mapped the universe, described its large-scale structure, and examined the formation, evolution, and dynamic interactions of galaxies and their stellar populations. Yet even with these advances, we encountered anomalies that challenged explanations within the framework of the Big Bang theory. Most notably, the absence of predicted relics such as magnetic monopoles or particles from grand unification led many to reconsider aspects of the theory. The universe we observe today seems to require forces beyond our current understanding. Despite these challenges, the expansionary model and its challenges persist. While existing theories fail to account for observed anomalies, two approaches have emerged: refine current theories or consider alternative explanations. The theory of inflation has emerged as the most promising framework for extending the Big Bang viewpoint. Inflation suggests a brief period of rapid expansion that smoothed the universe, giving it uniform properties. It addresses the horizon problem and predicts the development of quantum fluctuations, which manifest as density and temperature variations. The predictions of inflation align with observed patterns and changes, reinforcing its validity. However, despite alternative theories, inflation's scientific strength remains unmatched. Roger Penrose's work, alongside his collaboration with Stephen Hawking, failed to match the progress of inflation in explaining the earliest moments of the universe. Recently, efforts have been made to undermine the authenticity of inflation theory by supporting formal cyclic cosmology. However, this theory is inherently flawed from a scientific standpoint, as the key distinction lies in their predictions. Conformal cyclic cosmology proposes that remnants from a universe preceding the Big Bang are imprinted in the cosmic microwave background and the large-scale structure of the universe. In contrast, inflationary theory maintains that the end of inflation and the hot Big Bang are causally disconnected from any pre-Big Bang era. James Webb Telescope's amazing discoveries. Astronomers quickly noticed anomalies in the images sent by the James Webb Space Telescope starting in 2022. These revelations could require a reassessment of key aspects of the universe's origins and development. One major discovery made by the Webb telescope was the presence of fully developed galaxies much earlier than predicted by the standard cosmological model. This anomaly challenges the established sequence of events following the Big Bang, where stars and black holes form first, followed by galaxies. Such discoveries disrupt our understanding, like encountering grandparents depicted as children in a story. Furthermore, later evidence has revealed irregularities within major theories of the universe, such as the persistent error in determining the Hubble constant, which continues despite improvements in data accuracy and measurement techniques. New data from the Webb telescope presents challenges to the current cosmological model. These issues highlight imperfections within the model, raising questions among researchers and physicists. While the model has undergone changes recently to align with emerging data, some argue that these changes have been too accommodating. As a result, there is growing recognition that a change in perspective may be necessary, possibly reshaping our understanding of the universe's fundamental properties. The standard model of cosmology, hailed as a triumph of human knowledge, emerged from Edwin Hubble's groundbreaking discovery of the expanding universe during the 1920s. Subsequent discoveries, such as the detection of the cosmic microwave background radiation in 1964, confirmed the theory of the universe's origin as the most plausible explanation for the universe's beginnings, describing the early universe as a hot, dense soup of subatomic particles steadily cooling over time. Re-examining cosmology. Achieving the current level of precision in cosmological understanding has required theoretical extrapolation beyond observational data. The possibility of infinite expansion, introduced in 1981, was proposed to resolve anomalies in earlier Big Bang models, further emphasizing the dynamic nature of cosmological theory. According to this model, the early universe underwent rapid exceptional expansion shortly after the Big Bang. While specific problems are addressed by this theory, new challenges arise, particularly given the prevailing belief in the existence of a single universe. Perhaps there are countless others beyond our observational reach. Some observable anomalies, such as singularities within black holes, find support through indirect evidence. However, the stunning discoveries of the Webb Space Telescope regarding the development of galaxies and the ongoing issues with the Hubble constant raise concerns that we may be approaching a tipping point where a major revision of our current cosmological model becomes essential. This could necessitate a complete reassessment of the fundamental building blocks of the universe, including the very nature of existence itself. Cosmology, unlike many other scientific fields, deals with fundamental questions about the universe, its origins, and our place within it. The study of consciousness and quantum physics also investigates similar topics, examining the intersection of theory and reality. It is crucial to scrutinize these foundational assumptions, given the impact of theoretical presumptions on data collection. History has shown that shifts in scientific thought, such as the transition from geocentrism to heliocentrism or the discoveries of evolution and relativity, have led to significant changes in societal perspectives. A similar shift in our understanding of the universe may be approaching, driven by an impending scientific revolution in cosmology. Scholar Robert Anton Wilson argues that theory becomes essential when further scientific inquiry fails to provide satisfactory answers to a question. Investigations into cosmology may eventually lead to the breakdown of the current model, not due to observational errors, but because of its inability to embrace new principles that fully reflect the latest discoveries. The current narrative must therefore be reconsidered in light of new evidence, as the James Webb Space Telescope continues to uncover revelations that could forever alter how we understand the universe. Neil deGrasse Tyson, a famous astrophysicist and science communicator, made headlines with his remarks on the James Webb Space Telescope, JWST, in relation to the discovery of evidence suggesting the possibility of another universe. The JWST, launched in December 2021, is a powerful space telescope designed to explore the universe in infrared frequencies, allowing scientists to peer further into the cosmos than ever before. Tyson's comments stemmed from the extraordinary discoveries the JWST is already making, particularly in areas such as the formation of the earliest galaxies, stars, and exoplanets. While Tyson did not directly claim that the JWST has found evidence of a parallel universe, he referred to some of the astounding and unexplained phenomena observed by the telescope, which could point to something beyond our current understanding. One such anomaly is the presence of strange, unexplained patterns in the distant universe, which may suggest that the laws of physics as we know them could be different in other parts of the universe, or that the universe itself could be far more complex than we had previously imagined. This could imply the existence of multiple universes, as proposed by some theories in cosmology, such as the multiverse theory. However, it is important to note that while these observations are intriguing, they do not yet provide concrete evidence of another universe. Instead, they open up the possibility for new theories and ideas that could redefine how we understand space, time, and reality itself. As the James Webb Space Telescope continues its mission, it is poised to deepen our understanding of the universe in unprecedented ways. The data collected so far has already begun to challenge existing models and hypotheses, forcing scientists to reconsider some of the most fundamental principles of cosmology. One of the most exciting aspects of the JWST's discoveries is its ability to observe the early stages of the universe with a level of detail never before possible. With its ability to detect infrared light, the telescope can peer through cosmic dust clouds and examine distant galaxies, stars, and other celestial objects that were previously beyond our reach. This has allowed astronomers to observe the formation of galaxies in the very early stages of the universe, opening up new questions about the timeline and process of cosmic evolution. The Webb telescope's observations of distant galaxies suggest that they may have formed much earlier than previously thought. This challenges the established view that galaxies took billions of years to form after the Big Bang. The discovery of these ancient galaxies raises intriguing questions about how such complex structures could have formed in the early universe, and whether there were conditions or processes at play that we do not fully understand. This is just one example of how the telescope is forcing a rethinking of the standard cosmological model. In addition to studying the earliest galaxies, the James Webb Space Telescope has also provided valuable insights into exoplanets and their atmospheres. The ability to study the chemical compositions of distant worlds is a major breakthrough in exoplanet research. By analyzing the light passing through an exoplanet's atmosphere, scientists can identify the presence of specific molecules, such as water vapor, carbon dioxide, and methane. This could have profound implications for our understanding of habitability beyond Earth, as it provides clues about the conditions that might support life on other planets. Some of the exoplanets that the telescope has studied show unexpected features, such as unusually high levels of methane or other compounds that are difficult to explain based on current models of planetary formation. As the telescope uncovers more anomalies, it's becoming clear that the current cosmological model might not be complete. New discoveries could require a rethinking of the laws of physics as we know them. For example, the possibility of a multiverse, an idea that was once considered purely speculative, may begin to gain more traction as we observe phenomena that do not fit neatly into our understanding of a single, self-contained universe. This could lead to a radical shift in our understanding of space-time, gravity, and the nature of existence itself. Moreover, the potential for the Webb telescope to detect signs of dark matter and dark energy, two of the most mysterious and elusive components of the universe, could unlock new avenues of research that have long been shrouded in mystery. Understanding dark matter and dark energy is crucial to understanding the large-scale structure and behavior of the universe. These discoveries could also have profound implications for fields outside of cosmology, including fundamental physics, quantum mechanics, and even the study of consciousness. As the James Webb Space Telescope continues its groundbreaking work, it is clear that we are on the brink of a new era in space exploration and cosmology. The telescope's discoveries may not only answer some of the most profound questions about the origins of the universe, but also raise new questions that could lead to even deeper and more revolutionary insights. We may be witnessing the beginning of a scientific revolution, one that could change our understanding of the cosmos forever.